Welcome to micro communication course. Today we see horn antenna here. Horn antenna means what? That radiate element in the antenna is of a horn shape. Okay, means what? We say that the radiating element, this is about a shape of the antenna or shape of this radiating element in the antenna. That's why based on this structure or a shape, so that antenna or this type of antenna is called as a horn antenna. Okay, that radiating shape is about a horn-like structure there. Now, if you see the structure of the horn antenna, so it is just like a waveguide, and one end of the waveguide is about a flared out. Okay, it is just like a structure of a waveguide here, but one end of the waveguide is a flared out. So that's why it is called as a what you can say that a that structure is called as a horn antenna. Now there are the various types of an antenna here, various types of a horn antenna. So what are the various types of a horn antenna? One is about a sectoral horn antenna. Okay, we say that various types of horn antenna. One is about a sectoral horn antenna. Another is about a pyramidal horn antenna. Another type is about a conical horn antenna. These are about the three types of a horn antenna. One is about a sectoral horn antenna, pyramidal horn antenna, and a conical horn antenna. Now, if you consider that a sectoral horn antenna, that sectoral horn antenna, it has the two types. That two types means what? That structure it has in a antenna because it is a waveguide now. So for the waveguide, it has a electric field component vector as well as a magnetic field component vector along the size, okay, that height or the size of the particular waveguide there. So according to that, that sectors belong to the different plane. In that case, we say that it is about a E-plane sectoral horn antenna, or we say that it is about a H sectoral horn antenna. Okay, so means based on the uh, that sector, while sector means what? Based on the whatever the planes we have. So now, if you consider that a normal horn antenna, that is about a pyramidal horn antenna. Pyramidal horn antenna means it has a rectangular waveguide here. But if you consider that a conical horn antenna, that conical horn antenna it belongs to the circular waveguide. Means if we see the basic structure of a horn antenna, so in which it has a small waveguide, and that small waveguide is there. That one end is about just like one end of this horn antenna. That waveguide is about a open here. So I'll just draw a sectoral horn antenna first. Sorry, pyramidal horn antenna first, and then we'll draw the a sectoral horn antenna. So this is about our waveguide now. Okay, just like this one is about a waveguide here. But in the case of a sectoral horn antenna, what happened here? Sorry, in a pyramidal horn antenna, that here that end is about a flared one. Okay, just like we have the ends are a flared one. Means that both the A and B that size is increased here. Okay, so now this one is about a pyramidal horn antenna. If you see the waveguide, your waveguide will be looks like. Okay, now if you are able to see my screen here clearly now, I supposed to draw a small section of the horn antenna now. Sorry, waveguide now. Here, if you see the waveguide is how it is looks like. The waveguide will be this type of structure. In that case, this is about your A, that is width, and this B is about a height. Now this A and B, if you see in the figure here, so what is the A here? This will be the A, and this will be the B. Okay, so in the case of the in the horn antenna here, okay, if clearly one that width and height both are to be same here. Now this one is about A and this one is about a B here. In the case of a horn antenna, so this particular size is nothing but a A. Okay, this particular size here A, and this particular size about a B here. Okay, that particular dimension. If we say that A dash, because the dimension is different now. Okay, B dash. Okay, now this one is about a width of a waveguide, and this okay because this angle that what we say here that this one is about waveguide. The one end of this antenna is a flared one. Okay, that one end, this one is about a waveguide. This particular structure is about a waveguide. It is just like a waveguide, but one end of that particular waveguide, this end, it is a flared one. Just like I say that it is just like a flared one. Okay, that's about a flared one. So we say that in a on antenna that end of the waveguide is a flared one. Now this one is a normal rectangular waveguide, and that normal for a normal rectangular waveguide, this end is open, and this particular structure of a horn antenna is called as a pyramidal horn antenna. So in the case of a pyramidal horn antenna, that flaring is along the E side as well as along the S side. Okay, flaring. This is called as a flared one. That one end is a flared. So means it is flared with A as well. It is played along with A as well as along with a B. Means what? We can say that this vector as well as this particular side. Okay, means A and B. Means both the electric field component from this particular side that will be that side A is a flared as well as a B is a flared. Okay, so that is called as a pyramidal horn antenna. That pyramidal horn antenna, that is about a basic horn antenna, and generally it use a rectangular waveguide. Okay, only both the A as well as the H. Okay, that will be flaring along with the E side as well as the flaring along with the H side, and the shape is a truncated structure of a pyramid. So that's why it is called as a pyramid horn antenna. Next is about a circular, that conical horn antenna. Or we can in a conical horn antenna, that is about a circular waveguide with you. Okay. Now if you consider that a conical horn antenna, just like it has a circular waveguide, this one is about a circular waveguide here. But that end of this particular horn antenna, if you consider that uh, in the case of a circular waveguide here, so this one it is about a flared one. Okay, so this one is about a flared one, right? So what about this one? This one is about one end is about a flared one, in about a circular shape. This one is about a circular shape. So now this one is about a flaring one. What is the flaring angle? Flaring angle means what? The angle, how much is the flare takes place here, and that is called as a flaring. Okay, that is called as a flaring angle. Okay, this one is about a theta is about a called as a flaring angle. So now that what is the role of that particular flaring? Okay, we'll see in a detail. We'll just consider first a conical horn antenna. What are the various shapes there? Now this one is about a conical horn antenna. It use a circular waveguide. This one is about a section of a circular waveguide. Now this one is about a section of circular waveguide, and this end of the waveguide, circular waveguide, is a flare one. So it's just like a shape. If you see the shape, it just like looks like a cone now. That ice cream cone, if you have seen, it's just like a cone type of structure there. Okay, means what? That walls of the circular waveguides. Okay, sorry, the thing, but this one is about a circular shape. The walls of that circular waveguide are flared out, and that's why that antenna is called as a conical horn antenna. So in a conical horn antenna, if you see that what we can say that a circular one, circular, it has some particular dimension. Okay, that's diameter here. The same here, it has some particular diameter. That diameter is increased now because of that a flaring, and this is about a flaring angle. Okay, that is in a conical antenna. But in the case of a supposed to be pyramidal horn antenna, that flaring angle, if you see that, just like I supposed to consider that one side now. Okay, in that case, this one is about a flared one. And in that case, what is the flaring angle? Flaring angle is nothing but what? Whatever the angle that is called as a flaring angle is called as a theta here. This one, or in another say, this one is called as a theta here. That is about a flaring angle. And then that flaring angle, if you see the dimension from this, that it started with that open end, that is about a flare now. So this dimension, supposed to I say that this one is about the length. So in that case, we supposed to say that what is the length here? Okay, so length will be what? So this will be the same. That is about whatever the length we have. And this one is about a small dimension, that is about a increase. So that is about a path difference. If you consider that whatever the rays are propagating, okay, so that in that case, what will be the from this to the aperture? This is nothing but belongs to the aperture. Or this horn antenna is again a one of the type of the aperture antenna. This one is about the opening end is nothing but the aperture. And from the center, from this particular place, that is about the from this to this, okay, to the aperture, that is called as a axial length. And this is nothing but the whatever the aperture we have. So for the given aperture, it has some dimension based on the whether it is a pyramidal horn antenna, whether it is a sectoral horn antenna, whether it will be a conical horn antenna. Okay, that aperture is a different. Okay, so this L is nothing but the axial length, and this is nothing but the aperture dimension. I supposed to say that it is supposed to be D is the aperture dimension, and this flare angle is supposed to be a theta. Then the design equations for the horn antenna will be different based on the a theta here. Okay, now come to the topic that what are the various sectoral horn antenna. Now for the sectoral horn antenna, we supposed to know that A and B, okay, that is general waveguide we supposed to learn. Okay, so this one is about a waveguide now. Here for the waveguide, this one is about a waveguide, and for waveguide these are the these are the dimensions now. A and B, these are the dimensions of the waveguide. Now, okay, this one is about the B and this one is about the A. Okay, if supposed to be you are not able to see here, like right here, this one is about the B, this one is about the A dimension. Now, in a sectoral horn antenna, so which particular region we supposed to increase here? Okay, whether that is about the A or whether it is about the B now. So based on that, we say that a sectoral horn antenna. Now, these are about the dimensions we supposed to consider. Now, then A or B. So if supposed to be that flaring that flaring angle means what for a given waveguide, if we increase the this A and we supposed to fix the length that B is to be a fixed. Okay, B will be a fixed. This width, that height will be fixed. Only that we are increasing the A. Okay, so in that case A will be increased. So in that case, so what field vector is increasing now? So this one is about a magnetic field vector. Okay, so in that case, the plane of that H will be increased. So that's why it is called as a H sectoral or H plane horn antenna. Okay, so I suppose to consider that the dimension is a fixed now. These are the dimensions to be fixed now. Okay, now these are the dimensions here. If you see that this one is about a fixed dimension now. Okay, but we supposed to consider that this particular region. Okay, okay. Now this is called as a because this dimension is a constant. Only we supposed to increase this A now. This A will be increased. So now this is called as a H plane sectoral horn antenna. Okay, only that H size is increased. So that's why it is called as a H sectoral horn antenna. This B is a constant. B is a constant. That B is not changing. That height of the waveguide is a constant, only it will flare that A side. Okay, in that case, it has a magnetic field vector. Then the E sectoral horn antenna. So in the case of E sectoral horn antenna, we supposed to consider that this A is increased. Okay, now this one we supposed to consider that this one is about A is increased. So that is called as a E plane sectoral horn antenna. Okay, that this one is called as a E plane sectoral horn antenna. If you consider that in the case of a sectoral horn antenna, even if that only that this will be increased here, A is increased. Okay, so that is called as a E sectoral horn antenna, or we can say that a E plane horn antenna. If you are not able to see clearly there, I'll draw in another way also. Okay, so that you people are able to understand that what is the E sectoral. This one is about your normal rectangular waveguide. Okay, so in the normal rectangular waveguide, this will be increased now. I suppose to draw here. This one is about a waveguide now. So in that particular case here, both the sides are to be increased now. So in that case, this will be a fix now. Okay, whatever the what you can say that this in the A plane horn antenna, this one is about a E field vector. This one is about a E field vector. Okay, that is to be increased. So in that case, this will be increased now. So again here, latter now. Okay, this one. If you see here, so we have the asectoral horn antenna, right? We supposed to consider that this one is about a asectoral horn. So we can say that A size is increased. So that is called as a this one E is increased. So that's why it is called as a E plane sectoral horn antenna. Okay. Then we we need to find out that some of the operations how that flaring angle is there and how we need to consider that how that wave is going to be radiated in a space. So that propagating the signal, if you consider the waveguide now, so how your signal is going to propagating based on the what will be the flaring angle. So this one is about your waveguide. So what this one is about your aperture now, that aperture has a dimension d, and this one is about your length L now, and from this use a different one color so that this one is about the center now. You can say that this one is about a length L. Okay, okay, so this one is about length L here, right? This one is about length L here, and for this there is a flare angle. It is called as a theta. Theta is nothing but the flare angle. The wave is propagating, as we say earlier, for the rectangular waveguide, your electromagnetic wave is propagating. So this one is about your electric field component, that is about E here, and this one is about your magnetic field component, that is about H. So now that electromagnetic wave that is propagating in a waveguide Okay, that will be different from whatever the wave is propagating in the free space, because we have seen earlier that wave is propagating through the guide based on the mechanism of a reflection. Okay, so that's why your signal is reflecting from the conducting walls of the waveguide and then it will be propagating there. So in the case of a waveguide, we say that a propagation is restricted based on the whatever the conducting walls wave. And in the case of a, if you compare that a free space wave and a horn that whatever the wave is propagating through the waveguide, so in a free space wave, that wave is sprayed there. But in the case of a waveguide, wave is not sprayed because that wave is confined in the guide. Okay. But if that wave will reach to the one end of the rectangular waveguide, okay, one end is about now, right now it is about a flare one. So in that case, what will happen? That wave will be sprayed. Okay, if we consider only the rectangular waveguide, in that case, now supposed to be this one is about a circular waveguide. So if you give the input here, so now because of the confinement, whatever the wave is propagating through the rectangular waveguide, it will be same as it is because it is confined in a guide. But when it reach that wave is reaches here, so it will be sprayed. Okay, from this place, it will be sprayed away. Okay, but in the okay, similarly here, this to this is about waveguide. So because of the flaring here, flaring angle, one end of the waveguide is about a flare one. That's why at this particular region, then it will be dispersed or it will be spread here. Okay, so then that spreading that will be depending upon that what will be the flare angle here. Okay, spreading. So we consider that one end of the guide. Okay, so that will be about a flared one. In the case of a supposed to be guide, so it will be displaced anywhere, whatever the waves we have. Okay, it will be free to move. But because of this particular flaring here, the wave will be propagating through this. So it has a it's this wave front of the wave coming out of from the guide. It will be a different as compared to the open of the wave guide. Okay, so that so if you consider that a simple waveguide and their wavefront and a horn antenna and their wavefront, so it will be different because that end are different. So that's why the impedance is a different. Okay, so that's why we what we can say that here when the impedance of the waveguide and the free space impedance is not match here. So that's why it is not match because whatever the walls of the waveguide here that are a flared one. Okay, so it's two different cases. If you have only the waveguide and if you have a flared waveguide, then wave is propagating to this through this flared. So that and wave is propagating in the free space that impedance that doesn't match it. So that flaring, whatever we are supposed to be consider the flaring, that flaring provides the matching impedance. Okay, that flaring provides the impedance matching and as well as that flaring provides highly directive signal or that flaring provides the narrow beam of the signal there. Okay, so generally what we say that any antenna, what will be its wave front here, whether it is a plane wave front or what, okay, or uniform plane wave front or a circular. Okay, so whatever the wave front we have, if we consider the horn antenna, the horn produces a uniform plane wave front, whatever based on the whatever the aperture size, and that aperture size is depending upon that what are the dimensions of the waveguide here. Okay, that A and B size. If your aperture of the waveguide, aperture of that horn means that aperture means what? In the case of a pyramid horn antenna, this is nothing but a aperture. Okay, the case this one is nothing but a aperture now for the horn whatever the antenna we have. So this one is nothing but the aperture. So what will be the dimension of this particular A and B? That will provide you the what will be the size of the aperture there. And based on that aperture, so the directivity of the signal will be high. If the aperture is large, then the signal will be highly directive. Okay. If that aperture is small, that signal will be not directive as compared to the higher aperture. Okay, larger aperture. So in the case of designing the antenna, we supposed to know that what will be the length here. So based on that particular length, that aperture size will be increased or a decrease. Okay, that is one case. Another case is about that is about a theta. So means while designing the antenna, we are supposed to know that what will be the length here that is to be required and what will be the flaring angle. Okay, these two factors, that L as well as that a theta. So now we consider here how to calculate the value of this flaring angle, that is about a theta. That theta, if you consider that theta is depending upon that what will be the dimension, that is about a d here, this one is about a d, and what will be the length. And this belongs to the small del. Okay, this belongs to the small del. So we can calculate here theta is equal to what? A tan inverse of d by twice L. Or we can consider here twice of a cos inverse L by L plus small del. Okay, that is about a theta, that is about a flaring angle. And we can calculate that L, that is length, is equal to what? Whatever the aperture we have, that is about a d square by 8 of del. Okay, even we can calculate using the this one also, theta and L. This is about the aperture angle and L, or we can say that a flare angle. This one is called as a, we can say that this one is about aperture area, and this one is called as a flare angle. And that del is nothing, this del is nothing but what? Path difference we say. Okay, that is about del is nothing but a path difference. This one is about a path here for the given length. So that's why it's called as a path difference. And L is nothing but what we can say that a axial length. Okay, that L is nothing but the axial length. And D is nothing but what? Whatever the aperture we have, and for that aperture dimension, or we can say that generally people are using the word that is about the area. Okay, so here we say that a aperture dimension. Okay, next we need to find out what will be the half power beam width. Okay, generally we say that aperture size and a flaring angle will tell you what will be the directivity and what will be the beam width here. Okay, so now we need to find out what will be the a half power beam width. Okay, so if you consider the what will be the antenna, okay, so whether it is a pyramidal horn antenna or whether it will be sectoral horn antenna, so then the aperture beam, we supposed to know that what will be the half power beam width there. Okay, in that case we supposed to calculate that a half power beam width in the case of a E plane now. Okay, it is because E is nothing but for the E plane, so it is equal to what? A 56 lambda by DE. Okay, 56 lambda by DE. DE is nothing but what? The aperture in the E plane. Okay, that DE is nothing but what? The aperture in the E plane. Okay, and that is in a degree now. And phi h is equal to, that is half power beam width in the H plane. Okay, phi h is nothing but what? Half power beam width in a H plane. It is equal to what? 67 lambda by dh. That is in a degree. Okay, that's about a phi. And dh is nothing but what? A aperture, that is in a H plane. What is aperture? That is about dimension we say earlier. Okay, aperture dimension. And in the case of what will be the directivity there, because directivity is depending upon that, okay, aperture. If the aperture is large, okay, then directivity will be large. That's why we can say that a directivity D is equal to directivity of an antenna, that D is equal to what? A 7.5 A here divided by lambda square. What is the AA? AA is nothing but what? A aperture area. Okay. Whatever the physical aperture area here. So that is nothing but a AA. Okay, this one is what we can say that whatever the physical aperture area. Okay, physical aperture area. Aperture area. And that physical aperture area, if you calculate here, we can get that physical aperture area AA here is equal to what? What will be the DE here and what will be the DA. Based on that, that physical aperture area we can calculate. Then what will be the power gain? So power gain of this antenna here, it is equal to 4.5 A is nothing but the aperture area divided by a lambda square. Okay, A 4.5 A, even if you have here lambda square. Okay, right? See lambda. Okay, so this one is about a 4.5 A divided by the a lambda square. Okay, that is about what you can say that a horn antenna. And horn antenna, generally, if you consider that that antenna is used for the feeder, or as feed in a reflector, parabolic reflector or a dish antenna. So because that antenna has a plane wavefront there, or that is it has a highly directivity one, and it has a narrow beam width. Okay, so that's why these antennas to be used as a feed element in a parabolic reflector or a parabolic dish. Okay, next that if you consider that what are the features of this particular antenna, that features of this horn antenna are depending upon that what will be the a flaring angle there. Okay, if we say that whatever the flare angle, if that flare angle, if it is a small, okay, then your horn antenna will be a small there. Means whatever that it everything your antenna, we can say that antenna is about a small or a large. It is depending upon the a flaring angle. And because of this small horn antenna, that radiation pattern, it will be a very direct region. Okay, radiation pattern will be a very direct. So in that case, if you consider that a directivity, okay, in the case of a antenna there, so then in that case a directivity is small there. Okay, and that flare angle again it is related to the, or it is depending upon that what will be the axial length. Okay, so that's all about what you can say that a horn antenna. There are the different types of a horn antenna. That horn antenna, if you consider that a sectoral horn antenna, okay, that you can say that a pyramidal horn antenna and a conical horn antenna. In a sectoral horn antenna, E plane horn antenna and H plane horn antenna, and in the case of a that sectoral horn antenna, the dimensions or that plane, that everything whatever the antenna parameters are depending upon that what will be the dimensions there, and you can use the dimensions to calculate the whatever the directivity gain of the horn antenna. Okay, now in another case here, if you consider that in most of the book we supposed to use that a flaring angle just like a theta. Okay, that is about a flare angle. So in the another books they might have used, okay, so different dimensions or different relations for the flaring angle. Half of the portion is used to define what is the flaring angle and all. Okay, so that's all about the horn antenna. Horn antenna is again called as the aperture antenna there, because antenna radiation is depending upon that what will be the aperture size. Okay, that's why it is called as the aperture antenna. It belongs to the antenna category. And then if you consider that the aperture there, then apertures are nothing but what, a opening mouth. Okay, and in the case of a aperture there, if you see the field distribution, so field distributions in the aperture antenna, it can be what, a uniform one. Okay, so we supposed to talk about the electric field now. Okay, that is about a field distribution. That is about a near field heat distributions, or we can say that a aperture distribution. But if you consider that a far field pattern, okay, that is about a far field pattern means what, your radiation pattern. So in that case, that far field pattern will be what it looks like. It is about a one lobe here, and then we have the side lobes. Okay, that is about a far field radiation pattern. So that what will be the distributions there? If we have the uniform distribution, this one is that a uniform distribution, then we will get that here a far field distributions likewise. Okay, and if you have a distribution, if it is a circular one, or a cosine one, or a squared cosine, or a Gaussian one, then a far field distributions will be a different. So we need to find out there what will be the field distribution. Now this one is about a cosine, that's about half circle. So field distribution, that far field will be likewise. Okay, this one we say. And if we have the a cosine squared here, then we get the far field radiation will be a likewise. Okay, that is about a far field radiation. And then based on that far field radiation, we can calculate what will be the half power beam width and what will be its directivity of an horn antenna. Okay, so that is about what we can say that everything, that directivity is depending upon that what will be the physical aperture area of an antenna. That is about a D. We can say that a directivity of an horn antenna. Okay, so that's all about whatever the aperture that horn antenna is there. What we have seen today, we have seen that a sectoral horn antenna, conical horn antenna, and a pyramidal horn antenna. So thank you all of you. We stop here. Thank you all.